Hello and welcome to another video of Stat385. So we're gonna pick up, continuing on talking about coercion, which is something that we vaguely talked about last time when we talked about atomic vectors. Okay, so these are gonna be, let's see here. So we'll talk about introducing coercion of both type and length, and we'll talk about missing values, and we'll also talk about implicit versus explicit coercion, which explicit coercion we did a little bit last time when I went down a kind of a little bit of a tangent and accidentally typed an as dot instead of an is dot, and did like actually explicit coercion in that case, like changing a character number or a number that was expressed as a character into an actual numeric value. But then a lot of times you'll have implicit coercion, which creates a lot of problems. So let's go back to RStudio, or let's open up RStudio, and we have our little window here, or little panel to create code. We're in our Stat385 project, home, desktop, Stat385. You can see stuff here. Okay, global environment is clean, terminal is ready to go. Okay, so, as we saw last time, atomic vectors are homogeneous objects. That is, each element has the same type. So it's natural to ask, what happens if we try to mix different types? So let's just get going just a little bit here. All right, type of 42. So like we saw this last time, this is a double, and type of true, this is logical. Okay, so what happens if we put them in the same vector? So we've been claiming that vectors have, or we've been showing examples of vectors containing objects of the same type. So what happens when we combine them? Interesting. So what happened here? It looks like true was just converted into 1. Okay, so this would be an example of type coercion. Let's just further see it. So true got turned into a 1, and 42 was already a double. So this should be a vector with elements that are both doubles and should return double. In fact, it does. Okay, so the value 1 isn't too surprising here. Let's just see what happens if I switch it to false. I'm guessing that it will be 0. Yep, it is. Okay, so like we can always convert true false to 1 0, binary indication of true false. Okay, so let's continue on talking about explicit coercion. So I'm going to borrow some code that I have handy. Okay, so what I'm going to do is consider taking specific objects and converting them to logical. Okay, so, and seeing what happens. So the first one's pretty common sense, what you're gonna see, right? Like this is gonna turn the logical into the logical, so it should just stay true. Let's see what happens with the rest of them. Okay, so here it looks like all of the numbers are just converted to true, and R doesn't know what to do with a string. It doesn't know how to convert a string into a logical element, so it just gives up and just says NA. Okay, so not all types of implicit coercion will lead to some sort of meaningful statement. Debatable what meaningful means in this context, but nonetheless, R will sometimes throw up the white flag and just give up on it. Okay, however, that being the case, there are some strings, character objects, which can be converted to logical. So if I do this, for instance, it's converted to true. Same thing for here. Okay, so this is not something that, like, if you're operating on true false in this way, you probably have larger problems on your hand, but this is, of course, valid as we're just seeing here. One that we actually saw that was, again, going down the rabbit hole that I went down last time. If you had something like this, it converts it to numbers, which is actually kind of nice. Okay, so if I were to have a bunch of numbers, 1, 3, whatever, that's going to convert the whole. So, okay, what happened? So I have objects of all type character. They're all type character. So and if I'm combining them together, that is a vector of character type, and then I'm converting it to numeric. I could convert to double specifically if that's what I would want to do. It would give the same result. Okay, because double and integer have the same mode as numeric, and most for our day-to-day operations, we'll mostly just work with the numeric mode instead of explicitly the double or the integer type. Okay, so as I said last time, this kind of thinking is incredibly useful because oftentimes you'll be working, if you work with real data, you'll run into situations where for whatever reason a column of numeric values gets converted into type character when you load it into R, when you load that data into R, then you'll have to like turn it back to numerics. That's something that happens quite a bit actually. Okay, so I'm pretty sure that if we do any non-zero number, it'll always be true. Okay. And a zero number gets converted to false when we do explicit type coercion. Okay. Borrowing some more code. So let's see. Comment this out. Logical. Integer. Okay. So what happens if we force coercion for integers? What's going to happen? Okay. So we got an explicit error message that the string again, that NAs were introduced by coercion. Did we get that last time? Interesting. Yeah. So I guess that this is due to the nature of NA values, different NA values that we will get into as we go, as we move along. Okay, so we see here that true was converted to the integer 1, 42 remains 42, and as dot integer of a double just took the integer part. Let's see, just to make sure it's not rounding. Let's do 42.9999. Okay, so it just takes the integer part. All right, cool. And as already seen, if we have a object of type character, then it takes, so when we did as that integer, so I'm sorry, I'm operating on the console, not on my little panel for jotting down notes. So when I'm on the console, I can hit up arrow and go back through the commands I've listed. So yeah, as.integer looks like it converts it from character directly to integer provided that numbers are supplied, and then therefore pulls out the integer part, does like a few steps in one. As.double just takes the number directly. Okay. All right. And similarly, as.integer false, as.integer true, and we get 0 and 1. All right, great. Similarly for type double, let's borrow some convenient code that I have laying around and go through the explicit type coercions. So as that double for a logical, for an integer, for a double, and for a character. All right. Again, we get a message for NAs introduced by coercion. Interestingly enough, when we specify an actual integer and we convert it to double, we get 42.0. And here, yeah, with true, we also get 1.0 instead of just 1. Okay, so there's some slight differences in with as.integer, but basically the same pattern is observed, and we do get the warning message again, where NAs are introduced by coercion. Okay, so if we were to do type of, okay, so as.numeric, which is a catch-all for both integers and doubles. But however, it looks like what's going to happen is it's going to convert it to the more general category within numeric, namely the double. So a little bit of interesting thing to keep in mind there. Okay, so now we have character type, borrowing some code, again, that I have handy, and running through what happens when we do explicit coercion for logicals, integers, doubles, and character. Okay, so notice that there's no complaints. There's no NAs induced by coercion, whether the message was given to us explicitly or just it happened. So it looks like string is a pretty broad type that can handle all of the others, which kind of makes sense. We've seen this. We can write numbers as strings and the values true and false as strings. So I guess this isn't too big of a shocker here. So basically it just was easy to convert anything into type character. Okay. So yeah, so coercion character is definitely the easiest of these. Okay, so this is explicit coercion. We were very interested in converting objects of types, of different types, of one type to another type, and we were directly doing that because we wanted to, for whatever reason and purpose. And some of these are more to demonstrate kind of like the order of generality of these different, to show like what happens when you do it in all the different cases. And the other is to show some cases where it is useful, like for instance, converting numbers which somehow got represented as characters into numeric values, be it double or integer or just numeric in general. Okay, so now one thing that can happen, the other type of coercion is implicit. And so sometimes this coercion will just happen either naturally, or we can force it with just different operations. So let's see. So like here, I guess the noted difference between explicit and implicit is that I'm using an as dot statement to actually coerce an object from one type to another. And then here, this is going to be like either operator collisions or just accidents that can happen under the hood. This is something that occurs all of the time when you're writing functions, and when you're, I should say rather, when you write a function to perform a general task to a variety of vectors or data sets or whatever, when you test that function on different vectors and data sets, you inevitably will run into bugs for some sort of data set or vector that didn't initially conform to how you were thinking about writing the function. So this is something that I know I'm speaking rather broadly and generally. This is something that happens all the time. So implicit coercion is good to recognize because it happens all of the time. And if you don't have an eye for it, then you can waste a lot of time in your debugging, which I wish I had a class like this when I was learning coding, because I don't have a full account on how much implicit coercion has, how much time it has cost me, but I'm gonna guess in the order of days of my life. So, okay, so now we're learning it now. So what is implicit coercion? Stuff like this by operator coercion. I'm gonna just separate it out. Implicit coercion. Okay. So what happens if I do 3 plus true? Well, that seems silly, right? You can't have, this is something that doesn't make sense. So it shouldn't run chicken plain. It doesn't. It converted it to 4. So this doesn't make any sense, but as in art, but what is going on under the hood is that R is going to force this operation to take place. And so what R did was something like this under the hood. Okay, so as.double true, which we saw above, will actually return something, returns 1. And so it's doing 3 plus 1 equals 4. And, you know, sometimes this happens by choice. I've never used it before, but often it will happen when you least expect it, and it will cause issues. And, you know, to beat down this point, this general broad point I'm making when you're writing functions to perform tasks on data sets or vectors and making them as general as possible, it gets really complicated when you're doing statistical tasks when there's randomness involved, because if you get wonky results by adding quantities to them, you don't know if it's the product of implicit coercion or randomness. So things can get rather messy for you. Okay, so other examples. We did this, I actually did this in the last video. Actually, I didn't do it with a decimal. So this is like very easy to see as a type double, and this is a type integer. It's gonna just convert it to, coerce it to be type double. In this case, this kind of integer double type coercion happens all the time. We can also do stuff like this. So log, actually, you know, let's just check what the help page is for log before we run it. So uses, argument. So, right, actually, we haven't really gone into too many help pages yet. This one is gonna be really fast. So we sort of know what a logarithm is gonna do. If not, go to Wikipedia. Okay, so we have arguments. So this is what a function takes in. We covered arguments when we wrote some functions like that, calculate the rectangle or the perimeter of a rectangle and that other stuff. Okay, so it's taking in a numeric or complex vector, log. So here, we're just, you know, we didn't write x equals. We know that it's some value x. And here we're supplying it with the value true. I'm gonna guess, since it seems to be the case that if we convert true to a double or an integer, it's gonna be 1. I'm gonna guess this comes back 0. And it did, good. Okay, and then finally we have a case where, what's gonna happen here? No, gives up. Okay, good. So I'm not entirely sure why it gives up here. What I'm gonna guess is that string concatenation, like combining different strings together, is something that is a widely used different task than, you know, this sort of addition of two objects or numeric objects or objects that could be readily coerced into numeric, so that to build some separation there, it doesn't provide anything between string coercion and, you know, these sort of addition operations. Just a guess. Okay. So what's gonna happen if we do? I think we already saw something like this. Okay. So now we have a little bit of everything. We have a logical type. We have an integer, a double, and a string. So if we followed kind of, I don't like saying hierarchy, it's kind of the wrong way, but we saw that when we did as.character, for instance, these as.character calls tended to work, and we didn't need to, or we didn't observe any NAs. So I would guess that would be the case here. Yeah, I converted everything to string. Okay, just to try something, you know, we've been doing these in a kind of a natural order. Let's just switch it up. Yeah, same thing. So it finds, and let's do one more. Yeah, shouldn't matter the placement of the string. Okay, good to know though. All right, and if we do this, what's going to happen? Let's see. So true can be converted to a numeric type. I think it explicitly gets converted to double. Well, if you do as that numeric, it would. Okay. And double is more general than integer, so I would guess it would be double. Okay, looks like it. Yeah, because the true and the 1L got converted to 1.0, kind of this generic double notation. Okay. And we just see plenty of examples of this gets converted to a number. So integer. And any guesses for the last one? An atomic vector with one logical element should in fact be logical. Good. Okay. Missing values. So we've seen NAs. They've come up. Actually, let's go back a little bit here. Okay. So when we worked with logical, we got an NA value, but we weren't warned of it. And then in other cases, we got NA values and we were explicitly warned that NAs were induced by coercion. Okay. So one little caveat when we talk about missing values. So missing values, missing data are often, coded with an NA value, which is short for not available. And sometimes this is, missingness that just exists naturally in the data set. Sometimes it arises, as we just seen, and is induced by coercion or introduced by coercion. So I do want to say, and your book will point to this as well, that missing data is a subject or topic of statistics and data science, well known and important, and there's entire research areas devoted to best practices when you're confronting missingness. So for instance, it's important to be aware of the potential causes of missingness and the techniques to deal with the missing data if you diagnose the cause correctly. This can be a very deep theoretical statistical issue, and so it's not something that we're going to cover in our programming class, but it's something to keep in mind as you just get out there and are confronted with missing data in the real world. And in this class is going to be guilty of this, and other classes as well. We'll probably either remove missing data or treat it in some sort of ad hoc way to demonstrate programming concepts, but not necessarily to solve these issues statistically. Okay, so keep that in mind. Okay, so we've seen before that the NA value, type of, is by default logical. Okay, so how would it work if we were to do this? So we can see that the NA value is preserved naturally within a vector of doubles. Okay, so this is that issue that I was sort of hinting at when you have real data that has missing entries, like a CSV file with missing entries in it, and then you load it into R, and you want to do some data analysis, and then what happens is those missing values can get entered as just NA naturally into R. So it would be a problem if it was clobbering dimensions or something like that, removing the values or whatever. So so it just kind of just naturally appears as an NA value when you're using it. Nonetheless, that can be problematic. Okay, so we were sort of hinting at this earlier, that there's these different types of integer values. So for instance, there's NA character, so a missing character, and NA real, which is a missing double, and of course NA, which is just NA, and that's the logical type. Okay, so we could do option, okay, type of, okay. And we can see that, yes, that these different NA values are in fact of different types. Okay, so for instance, if we were to have a atomic vector with character type, with a character and an NA value, then, then we see that this whole thing will be type character. Okay, great. Similarly, if we have a double, get double, integer, and logical. Okay, great. So the NA values are just going to conform to the type of the atomic vector. So if I were to do, let's be a little bit fancy. Okay, what's going to happen? So I think that this will convert it into a character type. Yep. Okay, good. All right. So if we were to do operators or operations with NA values, what happens? So for instance, in this case, we should all just think that NA stands for I don't know. And I don't know plus anything is I don't know. I don't know. Something divided by I don't know is I don't know. Something times I don't know is I don't know. Doesn't matter if we really explicitly, if we really explicitly define what we know, but still multiply it by something we don't know, then we get something that we just don't know. Okay. So now here is an interesting case. I'll go through two. First one is going to continue this I don't know theme. Okay, so this is a vector, and it's going to complain and say that I don't know. All right, well, I didn't really complain, just said I don't know. Now, what happens if I were to do this? So one thing that, okay, so this is definitely getting ahead of ourselves a little bit here, but so R has a lot of built-in commands for, vectorized commands that we saw a little bit earlier, or last time. And so here I'm using one of those vectorized commands. Now normally in the examples I did last time, I did stuff like this, a little bit more shorthand, and you can see that it works on the vector. So this does what? This does the integer values from A to B, essentially all the integer values. Okay, so that converts, that creates an integer vector, and then we're summing all the elements, and we're not doing this with for loops, we're vectorizing it. So in this case, I had 11 elements, and one of them is NA, and then we had this usual case where when we're doing operations with I don't knows, then it just returns I don't knows. But a lot of these functions, these default functions in R, and what do I mean by that? So sum is a function in base R. You install R, you get the sum function for free. Remember, R is this comprehensive programming language for statisticians, by statisticians. I have software on R. Lots of people have software on R. And so that would be software you'd have to install directly. This is software that's given to you for free. So here we have, so we have the function sum, and a lot of these built-in functions have arguments for handling NA values directly. So in cases where, this is really kind of contrived, I created a vector of 11 elements. Take the time to see that's 11. But if you were to have some arbitrary column and some data set, the NAs could be relatively scattered. And even if you were to try to display some values of that data set to get a sense of what it looks like, you still might not come across NA. So this is great for handling that kind of situation where things get more complex. Okay, great. So let's continue on with more vectorization. Some things that I talked about in the last lecture as well. So this is something that I can't believe that we haven't declared anything to the global environment yet. Okay, so we're going to create a vector of integers, and we are going to assign it the name x. And I don't usually do this, but you can see if you wrap this in parentheses, that it will do the assignment and will print the results. I guess that isn't entirely clear because I already did the assignment. And this is cool. This does A to B, but it's going the opposite way. Okay. So here I don't have y in the global environment, so I'm going to take 5 to 1 integers decreasing this time, and I'm going to assign it the name y, and then with this wrapped in parentheses, it should just print. Okay, and it does. Okay, so now something that I did last time, adding two vectors with the same length, and it's going to add up the elements. It's going to do element by element addition. So the first element of x plus the first element of y, second element of x plus the second element of y, and so forth and so on. And I get the thing that I think that I would get. So under the hood, what this is doing is 1 plus 5 in the first element, 2 plus 4 in the second element, so forth and so on again. Similarly, I could do x minus y. Okay. And then I could do x times y, x divided by y, 7, x multiplied by y. Okay, so these all work nicely. And as we saw last time, I can use the same functions that essentially I used last time. I might demonstrate this point, that these built-in functions will work element-wise on vectors. Okay, log. And just to demonstrate, I can use function composition. Fun. Okay, so now one type of implicit coercion, which is very useful, is length coercion. And I did this last time, but I was not very precise in what I was doing. I kind of just treated it as like a matter-of-fact type thing, when really I should have been explaining it a little bit better. Okay, so I did something like this, where I have this vector of characters from 1 through 5, or sorry, numbers from 1 through 5, specifically integers from 1 to 5. Is it integers? I'm pretty sure it is. We did this before. We can always check. Great. Okay. So then I'm going to add 2 to it. And I did this last time without being very precise. So yes, this looks like this did exactly what I wanted to do. If my job was to add 2 to every element of the vector, then this did it. But this is actually length coercion that I exploited to my benefit. So what it's doing is, provided that, and I actually did see this last time because I also did something like this. And this would demonstrate the point well. Okay, now it complains. And so what's going on is a concept called recycling. Here we have 5 elements, and here we have 2 elements. And so basically what it's going to do is, if these things are multiples of each other, let's do it, then it'll work. But what it's actually doing is it's taking this thing and recycling it to fill it. So it's doing 2 plus 1 2, then 2 plus 3 4, then 2 plus 5 6. When it's a vector of length 1, this is really easy and will always work. But here we can see cases where it doesn't recycle correctly. Okay, so returning to this example, which I'm just gonna copy it. So yeah, it works great. But really what it's doing is something like it's doing this. Which is indeed the same. Okay. Right. So this works when it's multiples. So again, if I did this 1,6 plus C22, what it's actually doing is this. Okay, I have to be a little bit careful. Do this. So it's recycling it like that. And in my bad case, this doesn't work. Can't recycle this quantity correctly to get it to line up. Okay, so you do have to be a little bit careful with length coercion. Occasionally we can get away with it in very simple settings. Okay, and yeah, this is fun because this is kind of, I mean, I did a lot of copy and pasting, but this is a nice demo for the rep function. So, you know, now I'm gonna start over. 1,6 plus, instead of typing this 3 times and then wrapping it all and then combining it together with another call to the combine function, I can use the rep function to take my T2 thing, and then I can specify the argument times equals 3. Ta-da. Great, and it all works. Okay. All right, so you can always, if you get into cases like this, which can happen, recycling, again, we have 3 elements, 10 elements. You could do, say you do want to do the partial recycling 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. We could do rep 1, 3 times equals 3. Oops. Okay, so what is this going to do? So I'm going to take the the integer vector 1, 2, 3, and I'm going to repeat it 3 times, giving me 9 elements. So now I have a vector of 9 elements. Let's check it out. Yep. 1, 2, 3, 1, 2, 3, 1, 2, 3. And then I'm going to combine it with a single 1, and that gives us something to blame 10. So this all works. Okay, great. And if something is integer 0 plus 1 over plus this, so I have my integer vector here, and I add it to something that is integer 0, then I get nothing. Okay, so this is like the null type for integers. Okay, and of course, null being kind of a universal empty set for all the types, we get numeric 0. I wonder what happened, you know what? Just out of curiosity. Interesting. So doing a binary additive operator with a string overrides the idea that the null is just nothing. Okay, that cool. All right. Okay, so this is coercion. I know it's tedious stuff, but this is the root of a lot of evils with R programming. So it's important to know. Sometimes in cases like this, we get lucky, and sometimes we get cases like this where we get things. This type of thing happens all the time. You create some quantity that didn't satisfy some condition and was converted to nothing, and then you added it to something else or added it to some. Let's see what happens if you do this. Oh, it just got rid of it. Well, that's fine. But this type of thing happens a lot. And I do want to go back and highlight this explicit coercion where we did this as dot numeric and we have all these character with this character vector, because that's something that happens routinely to our benefit, explicitly converting strings that contain numbers to numeric type. And I'm being a little bit loose since we don't often distinguish between double and integer, but this should all be double, right? Okay, good. Okay. All right, so that is it for this video. Thank you for your attendance, I guess. Yeah, thank you and take care. All right, bye.